Last day before Christmas break is going to be spent talking about nuclear reactions or radioactivity reactions, but specifically about how quickly those reactions are taking place. I want to define a term for you that we're going to use throughout today called half-life. Half-life is the time that it takes for 1/2 of a radioactive sample to decay. Now, how do we know that it takes that long for 1/2 of a radioactive sample to decay? How do we know that it takes that long, one half-life, whatever that time is, for 1 kilogram of carbon-14 to decay into 0.5 kilograms of carbon-14? Well, the reality is we don't know exactly. This is based on probabilities. Radioactivity is a natural process. It's a random process. We can't predict when a particular nucleus will decay, but we know based on observation of decays that have already taken place, we know that in this amount of time, this half-life, each nucleus has a 50% chance of decaying. And if each one has a 50% chance of decaying in that amount of time, then on average, 50% of them will decay. We don't know exactly, but on average, 50% will decay. Let's say I start with 4,000 coins. I'm only going to draw 4. Each one represents 1,000. They're all heads. It takes me 1 hour to flip 4,000 coins. Got it? So if I flip 4,000 of those coins in 1 hour, we're going to say the half-life is 1 hour. Okay, that's statistically how much it's going to take for half of them to decay. Well, let's look at it a different way. If I flip each one of these coins in 1 hour, what are the odds of this coin becoming tails in that amount of time? 50%. What are the odds of this one becoming tails? 50%. The odds of all of these coins, of each of these coins, I should say, the odds of each one of these coins becoming tails after I've flipped it once, and remember it takes an hour to do that, is 50%. Well, if it's got a 50% chance of decaying into tails after 1 hour, then that means that odds are 50% of them will decay into tails after 1 hour. So we would have this after 1 hour, 2,000 heads and 2,000 tails. Now, is it possible that you have 1,999 heads and 2,001 tails? Of course it is. Of course it is. Each one has a 50% chance of decaying in that amount of time, which means on average, you're going to get half of them decaying. But you don't know exactly how many are going to decay. It's based on probabilities. We're going to make predictions in radioactivity just the same way. We're going to predict, given enough sample size, that after one half-life, half of it will have decayed. But you guys know that probabilities don't always work out, right? It's not always going to be exactly perfect. The bigger the sample size, the better off you are with your predictions. If you have 2 coins, each one of them have a 50% chance of decaying, right? But could you end up getting 2 tails after flipping them once? Easily, right? Odds are it's 1 and 1, but when you're only dealing with 2 of them, it could easily be 0 and 2. But if you're dealing with 4,000, odds are it's going to be 2,000 and 2,000, and usually works out to be pretty close to that, given enough sample size. So we take a radioactive sample, a big enough radioactive sample, it will take a certain amount of time for half of that sample to decay. The reason being is each nucleus has a 50% chance of decaying during that time. Now, there's a couple equations that we are going to give you that describe half-life. One of them, at least, a lot of you are going to recognize actually from math class. First one, probably the one that you're not going to recognize, but it's okay. It's a pretty intuitive one. Little n stands for the number of half-lives that have elapsed. Let's say that the half-life of element X is 3 years. 12 years have gone by. How many half-lives is that? The half-life is 3 years. 12 half-lives have gone by. Sorry, 12 years have gone by. How many half-lives is it? 4. Yeah, you say 12 divided by 3, right? The total time divided by the time for a half-life. Total time, 12 years divided by 3 years, the half-life, and we get the number of half-lives. The half-life is 2 days. 2 weeks have gone by. How many half-lives is that? 7. 14 divided by 2 is 7. The number of half-lives of little n would be 7 in that case. Little n stands for the number of half-lives. Unfortunately, that equation is not on your data sheet, but it's kind of a logical thing. Right? If you have 14 days total time, 2 days for a half-life, you don't even really need an equation to get the number of half-lives. Just figure it out. Now, the other equation is on your data sheet, and you probably recognize that if you've taken math 30. N is equal to n sub 0, 1/2 to the little n. This is your exponential growth and exponential decay equation. N, of course, little n stands for the number of half-lives. N0 stands for the initial amount, the original amount. And amount is the key word there, or one of the key words at least, certainly, because n sub 0 can be any units you want. Grams, kilograms, percent. It can be just a number. It can be a becquerel. A unit called a becquerel is a decay per second. It's just a unit of radioactivity. You don't really need to know about it. It can be any unit you want, as long as it measures an amount. An amount. If it measures an amount and it's the initial amount, then it's N0. Now, N stands for the final amount. This is what you got left at the end. And pretty flexible with units here as well. You just got to be consistent with the original amount. If you use grams, use grams. Kilograms, use kilograms. Percent, just a number, a becquerel, whatever. Just use whatever units you used for n sub 0. Those are my two equations. Done deal. There are situations where one of these equations becomes a little bit challenging to manipulate, to rearrange. We'll deal with that in a few minutes, but we're going to do a question first where we don't have to deal with that, where we just have to use the equations in a fairly simple way. So have a look at this one, please, on page 814. It says radium-222 has a half-life of 2.82 days. What percent of a sample of this isotope will remain after 2 weeks? Clearly a radioactivity problem, a half-life problem. In fact, we know the half-life is 3.82 days. That's a pretty short half-life, actually. Half-lives can vary dramatically from fractions of a second to millions of years. This is obviously somewhere in between, closer to a shorter half-life. If you had to be exposed to something with a long half-life or something with a short half-life, what would be worse for you? I mean, you don't want to be exposed to any of this stuff, right? Although on a daily basis, we're exposed to radioactive material and fallout from that, just that there's an acceptable range. Our body can repair itself quick enough to not have to worry about background radiation usually. So when we're exposed to higher levels that it's a problem. Let's say we are exposed to higher levels. Would you rather be exposed to a material with a short half-life or a long half-life? Short? How come? Because it breaks down faster? But doesn't it release more, does it cause more damage faster? Yeah, it's kind of a trade-off, right? Here's the thing. Let's say that there was some kind of radiological disaster. Let's say that was a radiological disaster in Okotoks. Okay, I'm not sure what would cause it, unless it was some kind of train or something. Yeah, there you go. Big rock, yeah. Yeah, I thought it was some rock off of a glacier in Jasper, and turns out it's a big chunk of uranium. Um, let's say that there's this radiological disaster in Okotoks. If there's a short half-life, then it means it's going to decay really, really quickly. The upside to that is, like in a couple of weeks, a few weeks, it's at safe levels. You don't have to worry about it. Like it's not going to take very long at all. Like a month from now, if the disaster happened today, a month from now, it would be absolutely safe to move back to Okotoks. No issues whatsoever. Probably even sooner than that. But the flip side of that is if you're exposed to it in the short term, the rate of decay is much quicker. So the damage done to you in the short term would be much greater. So I guess the deal would be if you can get out of town and avoid exposure, you want a short half-life. If you're going to be exposed to it right away in the immediate aftermath of the event that took place, you would probably want a longer half-life because it would buy you some time to get out of town. Yep. Yeah. What percent remains after 2 weeks? Well, our time here is 2 weeks or 14 days. Doesn't matter what units we use here, but we got to be consistent. Percent remains. What are we looking for here? Is that n or n sub 0? It's n. How much is left, right? How much remains is n. All right, let's try this equation. N is equal to n sub 0, 1/2 to the little n. We can find a little n by saying t over t 1/2. So we got, what, 14 days divided by 3.82 days? What does that give me when I do that math? 3.665. Thank you. So 3.665 half-lives. Now I'm going to plug that in here, and oh, what's little n? Or sorry, big N sub 0. What percent remains? What percent started? 100. Started with 100%. So we're going to say 100 times 1/2 to the little n, which is 3.665. Be careful with the math there, because this isn't times 10 to the 3.665. This is 1/2 to the 3.665. Let's pull out a calculator here. Let's solve this as a group here. 100 times 0.5. Now I'm going to press this little button right here under the clear button, the hat button. 3.665. 7.88. So after, what, 2 weeks? Only 7.88% remains. Now, if we go back to that hypothetical radiological disaster in Okotoks, radon 222 is our problem. After 2 weeks, you're down to less than 10% of what you started with. It's not going to take very long to get safe at all, right? Now, here's the thing that we didn't talk about. And a potential ugly reality in all this is that after 2 half-lives, yeah, you've got 7.88% of your original radon left. What replaces it? What did radon 222 decay into? Now, I'm not sure. I don't know what it decays into. But if it decays into something that's stable, it's all good. Okay, you got hardly any radioactivity left. But if it decays into something that is in itself radioactive, well, problem might not be over so quickly, right? Does that make sense? Okay, I want you to take a look at a couple questions that appear on page 814, please. All right, let's have a look at number 2 here. It says tritium. Look at what that is. H3. That's hydrogen, right? Normal hydrogen has 1 proton, no neutrons. Normal hydrogen nucleus, that is. Whenever we're talking about this isotope notation, we're talking about the nucleus, right? Not the atom. 1 proton, no neutrons. This has 1 proton and 2 neutrons. This is heavy hydrogen. Yeah, you can make water with H3 because chemically it's identical to H1. It's chemically identical to every other isotope of hydrogen. But it obviously, because it's 3 times the mass, it produces literally heavy water. Water that is much heavier than regular water. Water that uses the isotope H1, which is regular hydrogen. Okay? Tritium has a half-life of 12.3 years. How much of a 100 milligram sample of tritium will be left after 5 years? That is, it can make heavy water if it's H3 with electrons orbiting around it, right? Not just the nucleus, of course. You can't make water from that. How much remains of a 100 milligram sample after 5 years? So we're going to say T1/2 is equal to 12.3 years. We're going to say T is equal to 5 years. And what do we got here? N0 is 100 milligrams. We want to find out what N is, the final amount. So we're going to say N is equal to N sub 0 1/2 to the little n. We're going to find a little n by saying T over T1/2. That's 5 over 12.3. What did that equal for the number of half-lives there? 0.4065, thank you. There's the number of half-lives, less than one half-life. 100 times 1/2 to the little n, 0.4065. Let's figure that out as a group here. We got 100 times 0.5 hat 0.4065, and that gives me 75. Should be 75 milligrams. They say 75% here, but because you start with 100 milligrams, the percent in the milligrams would be the same number. So both are actually correct, but it should be in milligrams. All right, let's do another one here. This one's not in your book. It's a good one, though. The half-life of carbon-14 is 5,730 years. Remember that, write that down somewhere, whatever, because you need that in the check and reflect questions, and we're going to assign to you in a couple minutes here. You need that number. The half-life of carbon-14 is 5,730, as compared to radon 220 or 222, whatever it was, which is what, 3 days or something like that? This takes a lot longer to decay, right? How long does it take a 12.5 kilogram sample of carbon-14 to decay into 400 grams? The half-life is 5,730 years. N0, the original amount, is 12.5 kilograms. N, the final amount, I'm going to say is 0.400 kilograms. I could say 400 grams, but when I do a calculation, I want to make sure I'm in the same units. Grams could have worked as long as I use grams for both of them. I think we're just looking for T here now, right? So I know that N is equal to T over T1/2. So T is equal to N times T1/2. So I multiply the number of half-lives by the half-life, but I don't know what little n is. So what do? Go to my other equation, right? The other way to find N. N sub 0 1/2 to the little n. Anybody know how to find little n from that equation? How many people are taking Math 30 again? If you've taken Math 30, you probably know how to find it. What's the answer to that question? Logarithms, right? If you haven't done it, don't worry. There is another option. And I'll show you what that other option is in a couple minutes, okay? So using logarithms, we're going to say little n is equal to log n over n0 over log of 1/2. So I took the n0 over by dividing. I get n over n0 equals 1/2 to the little n. And I'm going to log both sides here. So that ends up being what? Log 0.4 over 12.5 over log 1/2 or 0.5. Okay, let's figure out what that is. On our calculators, let's say log 0.4 divided by 12.5. Let's end the bracket there and press enter. And then let's divide that by log 0.5, end the bracket there. 4.97. That's my number of half-lives, which I can now turn around and multiply 4.97 times the half-life at 5,730. And we end up getting 28,453 or 2.84, 2.85 times 10 to the 4 seconds. Years, sorry. Good. So you're not comfortable with logarithms, then what I did on the right-hand side isn't going to make a lot of sense. But does it make sense if you can get n, how to solve this problem? Because I'm going to give you another option for finding n here. It only works if n is a whole number. It's not quite a whole number here, but it's darn close, right? What you have to do in Physics 30 is, and this is exactly what they say in the curriculum, you have to perform simple, non-logarithmic half-life calculations. I don't like the word simple in there because the questions aren't always simple, but they are always non-logarithmic, or at least they can be. Okay, there's always a way to solve it not using logs. Let me show the other way of finding little n, the number of half-lives. I call it the divide by 2 method. Create a table with 2 columns, n and n, little n, big N. After 0 half-lives, right, this is the number of half-lives. After 0 half-lives, we've got 12.5 kilograms of this radioactive sample. Nothing's decayed, right? After 1 half-life, we're going to keep dividing by 2 here. After 1 half-life, I end up with 6.25 kilograms. After 2 half-lives, keep dividing by 2. 3.125 kilograms. Keep dividing by 2. Another half-life, we get 1.5625 kilograms. After 4 half-lives, divide by 2 again. I get 0.78125. Keep dividing by 2 again. Divide that by 2, we get 0.3906. How do I know to stop there? How do I know to stop after I've divided it 5 times? I want to get down to 0.4 kilograms. I get down to essentially 0.4 kilograms, 0.3906 kilograms. So I'm going to say here that n is equal to 5. And I'm going to say t is equal to n times t1 half, which is 5 times 5730. And when I do that, I get 20,650, or 2.86 times 10 to the 4 years. Now, you get a question like this, you're comfortable with logarithms, do it that way. Do it that way, it's fine. I'm not a big fan of logarithms myself, but never liked them since I was in high school. But if you're good at it, you're comfortable with it, go ahead and do it that way. But you can also keep dividing by 2. Now, in this case, you see we got a slightly different answer. I don't think that would happen on a diploma exam. I think they'd give you an exact whole number so that it wasn't 4.97, so that it was exactly 5. But even if we did have a situation like this, if it's a multiple choice question, you can tell which one's the answer, right? You get 2.86, the answer is 2.85. Oh, well, it's the answer. They're not going to give you both of these as options. Or if it's numerical response, I suspect what they do is make it a 2-digit answer. And a 2-digit answer becomes 2.9 and 2.9. So it ends up being the same either way. Or if they made it a 3-digit answer, they'd accept both answers. Okay, so don't worry about that. Use whichever method you find most comfortable. You'll get the right answer that way. All right. I want to give you a graph here, and then I want to give you a few questions to work on, and then I am done until after Christmas. This is what we call a radioactive decay curve. You can see on the y-axis is counts per minute, but it doesn't have to be counts per minute. It just has to be some unit for n. It could be grams, kilograms, percent. It could be counts per minute. Counts per minute. It could be just about anything. In this case, it happens to be counts per minute. No, it couldn't be coulombs. On the x-axis, you have time. Every radioactive decay curve you see will look like this. It doesn't matter your data. It doesn't matter what number you start it with. It doesn't matter what units you have on the x-axis or on the y-axis. The shape of every radioactive decay curve will look like this. Now, the bad news is this is not a linear graph. You go to try to analyze this, you can't use y equals mx plus b. It's a logarithmic graph. That's a pain. The good news is the only thing you have to do with this is a couple of situations where you have to read numbers off the graph. Let's say I ask you, how much remains after 4 days? What's N? How many counts per minute do we have after 4 days? What do we do? Easy. Go to 4 days, go up and over. How much remains after 4 days? 20. 20 counts per minute. What if I said, how much time does it take to get down from 80 to 10 counts per minute? Well, we'd go over and down. Looks like about 6 days. So you either go up and over or over and down, and that's it. That's all you can do. Here's the hardest one. What if I asked you what's the half-life of this material? What's the half-life? Sorry, Matt? You'd go to 5 days, did you say? No. Why do you say it's 2 days? Good. What's important here is that we go from 80 to 40 in one half-life. And then we're going to go over from 40 and down, and it looks like about 2 days, just a little bit before 2 days. Does that make sense? Up and over and down, whatever it is that you're looking for. If you're looking for N, go up and over. If you're looking for T, go over and down. Now, it matters where you start from, right? If you're looking for the half-life, you got to start from 40 there. Okay, but in the end, it's still over and down. All right. Here's what I would like you to work on now. All I'm asking you to do here on this page, on page 817, believe it or not, brace yourselves here, is question number 1 and 3 to 7.